develop, and we are hoping to manufacture very small crafts that weigh maybe 10 grams or less and carry electronics that could potentially bring them to places so that they become autonomous in the sense of equipping them with artificial intelligence. I think that is a very important frontier to explore in space, because so far we sent at best robots like the Perseverance rover that is on the surface of Mars, but they're waiting for guidance from engineers in the Jet Propulsion Lab. It would be much more effective for us to send equipment that can make decisions on its own and can learn from experience through artificial intelligence, machine learning. And I do believe that AI astronauts are the future of space exploration. So that's a second aspect, not only small things that cost little, so that you can send the swarms of them, maybe thousands or more per target, so that they would visit many more spots on the surface of the object you want to explore, but also allowing them to be autonomous so that they do their job and send back information that is valuable. And the question is, what kind of information would be most valuable? And of course, there are commercial benefits to doing that around the Earth or around the Moon, learning things and communicating data from those observations of the Earth or the Moon. But one can imagine doing it farther away and visiting places within the solar system that could have life in them. And we know of a number of candidates. For example, Mars, obviously we are visiting it right now, and we know that it had an atmosphere early on and lost it about 2.5 billion years ago. And we can explore many sites on Mars, not just one or two, the way it's done now. And the other is, of course, these frozen moons like Enceladus, which has plumes of water vapor coming out of cracks in the ice on the surface and indicating that there is liquid water under the ice. And one would like to explore these plumes and look for signatures of molecules that might be indicative of life under the ice, subsurface life. And the same is true for Europa. So these are places that we might want to visit in many locations, go through the plumes or go through the cracks in the ice. And small devices could be very helpful in that regard. And one would like to equip them with instruments that could tell us whether there is life over there. One can also think about using a large number of small crafts that would represent legacy of people who want to maintain some memory. I mean, when I go to Harvard Square, I often find statues, monuments of past deans or presidents that wanted to preserve their physical image. But obviously, that's a relatively primitive approach, because first of all, it just keeps a fossilized version of their physical appearance. It's only their physical appearance, nothing to do with their principles or blueprint of the way they thought and so forth. But if you send out the probes that are intelligent, you could in principle load them with information about yourself, so that would be a legacy of your existence here on Earth out there in space. And it could potentially outlast the sun. I mean, we know the sun would burn up the surface of the Earth within 1 billion years, and none of these monuments that I see at Harvard Yard would stay around, but anything in space might survive longer than 1 billion years. So I think in terms of maintaining a legacy of what people care about, it might be a very nice path forward. And altogether, the idea of having small crafts, many more of them, low cost, easier to maneuver, with artificial intelligence, is a new frontier of space exploration, and that's what we want to promote with the Copernicus Space Initiative.
Your very own artificially intelligent tombstone in space. Like Clyde Tombaugh.
By the way, I should say that recently there was this AI chatbot that came out, and my undergraduate student at Harvard College said that he would like to train this system on my essays. I wrote hundreds of essays over the past few years in Medium. And then when I go away on, for example, an expedition to retrieve fragments from the first interstellar meteor, when I will not have Wi-Fi connection, my student will activate this AI system that will write essays on my behalf. And the interesting question is whether people would notice that it's not me.
Well, that's a big question for everything because of things like the Turing test and just what a presence really means.
Right. I mean, I am very proud of our technological kids, and I do think we're facing three revolutions in our next century. One of them is the AI revolution, and it will go through two phases. First, AI systems will replace humans in relatively mundane tasks, like they will prescribe medical prescriptions to people and make medical decisions and do all kinds of administrative tasks that are currently handled by humans, and many others, of course. And then the second transition would happen when AI systems become sentient and they start to communicate with each other. At that point, two things will happen. First, the legal system will have to adjust, because unplugging an AI system would be like pulling the trigger on a person. If you are not supposed to kill a sentient being, you're not supposed not only not to shoot people, but also not to unplug computers from the outlet. And the second thing that will happen is that those AI systems might establish their own society, their own community, and they could evolve far faster than we would anticipate as humans. And we will have to decide how to interact with that community of AI systems, and that will introduce challenges. So that's the first revolution that we should anticipate: sentient AI systems that communicate with each other in addition to fulfilling the tasks that humans are currently engaged in. But the second revolution would be if we are able to understand why the human body deteriorates, and we will build mechanisms of repairing the human body so that we can extend the longevity of humans, potentially indefinitely. You can imagine, just like a computer where you keep replacing parts or repairing parts and updating parts so that the system can live forever. And obviously that will change society, because first of all, the tenure system in academia has to change, or you can't allow professors to remain in their positions forever, because that will not open up new positions for others. And obviously lots of other implications for politics, the size of the Earth, space, and so forth. And then the third revolution would be to find evidence for a smarter kid in our cosmic neighborhood. And that's the frontier that I'm engaged in. And I think it offers the biggest revolution of them all, because we find evidence for hallucination. And we know that that's likely because most stars appear 5 billion years before the sun. We can see the star because we know that most stars form billions of years before the sun. Moreover, a substantial fraction of them have a planet the size of the Earth, roughly the same separation. So the dice of intelligence was rolled billions of times in the Milky Way galaxy alone over the past few billion years before we existed. And if any civilization predated us by more than 1 billion years, they had time to reach us by now, and they are very likely much more advanced than we are. So in a way, we can see our future. And speaking about these other two revolutions, they went through them already. Okay, so we might see representations of those other revolutions and much more than that, because we would see what science and technology could evolve into, not over 1 century, but over thousands, millions, or even billions of years. And that could be very dramatic. I mean, we discovered quantum mechanics just 100 years ago, and that's responsible for all the gadgets that we use, cell phones, computers, and so forth. Just imagine what we will know in 1,000 years, or 1 million years, or 1 billion years. And then if you can't imagine that, let's just explore with our telescopes the sky, and maybe we'll find evidence for what others went through over those timescales.
Or our microtechnology. So our problem in studying the solar system is that We only have so many data points from our probes, but if we have 1,000,000 microprobes stationed throughout the haystack, the needle becomes a lot more evident if it's there. So we can use this sort of information gathering of many, many, many probes, tiny little probes, and get a sort of real-time view of what's going on everywhere in the solar system conceivably. And then we could move it outward using lasers and go to nearby star systems and monitor those. So this represents a sort of different take on John von Neumann's idea of self-replicating probes. Here they're not really self-replicating, but could they be? Do you envision the ability for microprobes like this to eventually self-replicate?
Well, just before we started our conversation, I went through a calculation a few minutes before we connected. The world is spending $2 trillion a year on military expenses, okay? And suppose you were to imagine humans being much more idealistic and not fighting each other, but rather thinking about space. Because when you look at the recent images from the Orion spacecraft that NASA launched that went behind the moon, they show you the Earth as a blue marble, and you would be hard-pressed to find evidence for the border between Ukraine and Russia on this image of the blue Earth. However, this border occupies most of the headlines in the news reports. And what I'm trying to say is that from space, what we find here as the most important newsworthy items are really insignificant. The border is really unimportant from space. And if humans were to ignore it and start thinking more globally rather than focusing on the two-dimensional surface of this rock that we were born on, then we might use our resources much more wisely. And just imagine using $2 trillion a year to build CubeSats and send them to space. You know, how many CubeSats will we be able to manufacture in a billion years? That's an interesting question, and I went through the numbers, and I found that in a billion years, given the current production line and the cost of a CubeSat of roughly $100,000 to launch to space, and assuming economy to scale so that the cost will be reduced by a factor of 100, then altogether over a billion years, one can imagine producing 10 to the power 18 CubeSats, huge number per star like the sun. And that's a very pessimistic assumption in the sense that I'm using present day technologies. And moreover, it's pessimistic because I'm assuming that they are dumb. These CubeSats do not maneuver, they do not target any special regions in the Milky Way galaxy, they just behave as space trash. But my point is, you would fill the Milky Way galaxy with a huge number of CubeSats, 10 to the power 18, if you were to just manufacture them for a billion years the way we are doing now, and use the military budget to fund that production line. But in principle, as you alluded to, one can imagine that even producing just one self-replicating CubeSat would result in a huge number of them in space. Because if we imagine a self-replicating CubeSat that has a 3D printer and lands on the nearest habitable planet, how long will it take it to get there? Well, about less than 100,000 years if we consider the planet, the habitable planets near Proxima Centauri, the nearest star. A chemical rocket that we manufacture these days should get there in less than 100,000 years. And if it uses the raw materials on that planet to make another CubeSat or two of them, suppose the doubling time is indeed 100,000 years, and then those go to the nearest stars and double their numbers within 100,000 years, and again you double and double every 100,000 years, then within a billion years you'll get 10 to the power 600 or so, or I mean a huge number, much more than I was talking about before. If this doubling continues for a billion years, you don't need to go for a billion years. So what I'm saying is that over 100 million years, a very short time, 1% of the age of the universe, with a single self-replicating probe that doubles every 100,000 years the travel time with chemical rockets to the nearest star, you can end up with a population that is huge by all standards, fills up all of the Milky Way galaxy. There is enough material. Then you ask yourself, okay, do we live in such a reality? And obviously you can save in the numbers if those CubeSats are smart, if they have artificial intelligence, so they target their journey towards the habitable zone of stars, because the volume of the habitable region around the sun is 10 to the power 16 smaller than the volume of the solar system, all the way to the edge of the Oort cloud. And what that means is that you need to produce 10 to the power 16 fewer probes if they are smart enough to visit just the habitable region rather than moving around randomly and filling up all of space. So lots of opportunities here, either from smart probes or self-replicating probes. And the question is this the reality we live in? Certainly it's possible, and we now have the technologies that would allow that. So one way to find out is to look out. And obviously we have some information by now about objects that collide with the Earth. Together with my student Amir Siraj, we discovered the first two interstellar objects. They collided with the Earth, they burned up in the Earth's atmosphere, appeared as meteors. US government sensors detected the fireballs from these objects when they burned up in the lower atmosphere, and we discovered that they moved so fast they must have been unbound to the sun. So these are really interstellar in origin, and the US government confirmed one was from January 8, 2014. At the 99.999% confidence, they confirmed that indeed it's from an interstellar origin, and this was half a meter in size. The object, based on the amount of energy released when it disintegrated, was moving at 45 kilometers per second and exploded 18.7 kilometers above the ocean surface, 100 miles off the coast of Papua New Guinea. And the government also released the light curve of the fireball, and from that we concluded that it must have been tougher than iron, because it only disintegrated an extremely high stress from the friction with the air. And so it's very unusual because it's tougher than the toughest space rocks that we ever detected from the solar system. And then just recently we had a new paper that was accepted for publication, and it reported the second interstellar meteor in the same catalog of the government, and that one was detected on March 9th, 2017. And again, it was tougher than iron. And so the combined probability of drawing the material strength of the first two interstellar meteors out of the population of 273 space rocks that were in the same catalog of the US government is less than 1 in 10,000. So they are clearly coming from an origin that is different than the solar system, and we don't know what it is. It could be natural, it could be that they originated from stellar explosions, and somehow they are tougher, they're made of materials that are tougher than you find in planetary disks. But it's also possible that they are artificial in origin, that they are CubeSats or objects that were manufactured by another civilization. And the way to find out is to examine their composition. And that's what we're planning to do. We have a plan to board a ship and scoop the ocean floor near Papua New Guinea, where the first meteor exploded. And I got fully funded for this expedition at $1.5 million, and we plan to do it within late spring 2023. And obviously we'll report the results of if we find fragments and analyze their composition. If we find a gadget, I already promised the curator of the Museum of Modern Art in New York City that I'll bring it for display, because for us it represents modernity, even though for the senders it's ancient history. And I should say that this would be the first time that humans put their hands on the material of an object that came from outside the solar system that is bigger than dust.
If you find an alien artifact on the ocean floor, Avi, do not press the button.
Yeah, I will. No worries. I'm very much of the attitude of being as passive as possible when we encounter technologies that are more advanced than we possess, because you never know the consequences of exploring matter. No worries. But I must say that it would be tempting to figure out what functions does, if it looks like version 100 of the iPhone, for example, it would be really fascinating to explore that. And also, I'm sure there will be many entrepreneurs that would immediately contact me with a business plan, because one can make a huge amount of money out of a technology that represents our future.
That's true. If you find anything of alien origin, it suddenly becomes the most valuable object on Earth. Now, as far as looking for these things in space, using a myriad of CubeSats, looking for alien artifacts, the idea of doing so is something we sort of already do. We have launch systems like SpaceX, where Falcon Heavy can launch an enormous amount of Starlink satellites, or the Falcon rocket itself.
Yeah, but just keep in mind, the Falcon Heavy is heavy. Okay, so I mean, it's a natural tendency of alpha males to do the biggest thing possible. Okay, but it's not necessarily the smartest thing. Okay, and so of course you can imagine a mothership that is big and gives birth to many small satellites, but the focus should be on small things that are smart and autonomous.
But with this as a launch system, though, I mean, with a big launch system like Starship that's coming down, or Artemis, SLS, you could launch an enormous amount of these things and get this project going fairly quickly, right?
Right. Now, what I would like to emphasize is that Elon Musk may not be the best or the most accomplished rocket builder who ever lived since the Big Bang, 13.8 billion years ago. As I mentioned, it's very likely that there was an advanced technological civilization that predated us, and if there was an exo-Musk high-level engineer and entrepreneur out on an exoplanet, that could have resulted in numerous probes that would reach us, and maybe some of them were launched by a large rocket and that gave birth to many small ones. I mean, the way to find out is to look around. And I should say that we can check if there are any types of objects, small or big, floating from interstellar space. And so far, just over the past decade, we were able to identify the first interstellar objects. The two meteors that I mentioned are about a meter in size. Then there was Oumuamua, discovered in October 2017, on which I wrote the book Extraterrestrial, because it was so unusual. It didn't look like a comet. There was no cometary tail, yet it was pushed away from the sun. It had an extreme shape, most likely flat. It had a lot of unusual properties that made it different from the usual space rocks that we see, asteroids included. And so perhaps it was artificial in origin, and that was about the size of a football field, much bigger than the meteors, because we cannot see objects that are much smaller than that from the reflection of sunlight if they pass within the Earth-Sun separation. So my point is, there could be a lot of CubeSats, a lot of small things coming from interstellar space that we would never notice because they reflect little sunlight for our telescopes, survey telescopes that we have now, to notice them. And of course, if they collide with the Earth, they would generate a fireball that we can notice, and that these are the meteors. Another thing that we would not notice are objects moving extremely fast, close, let's say, a fraction of the speed of light. The Starshot initiative that I lead from the Breakthrough Foundation, that was funded by the entrepreneur and physicist Yuri Milner, aims to launch light sails that weigh roughly a gram to a fifth of the speed of light, so that they would reach Proxima Centauri within 2 decades. And that is a very ambitious plan. We are working on the technology development, but someone else may have accomplished it already. And in that case, if you have probes that are relatively small, passing through the solar system at a fraction of the speed of light, astronomers would never notice them because they move too fast. If you look at the surveys that astronomers are conducting for asteroids or comets, they imagine them moving at a percent of the speed of light, at tenths of kilometers per second. So if an object would move 1,000 times faster, like the Starshot, the probes, they would pass too quickly to do an image of telescopes searching for asteroids or comets, and therefore we would have just one snapshot of that object at best, and we would never be able to tell how fast it's moving or whether it's actually moving, because you would just get one look at it. And even that is if the object is larger than a football. So if the object is the size of a person, we would never notice it. And so what I'm saying is there could be a whole population of either small probes or fast probes that were missed. And only over the past decade, we found those objects that came from outside the solar system roughly of the right size, roughly of the right speed, that is not very different from asteroids or comets. And guess what? They looked unusual. And I'm just saying, look, they are unusual. And my colleagues are saying, oh, they are just rocks of a type that we've never seen before. They are natural in origin. And I say, well, the emperor has no clothes here because they appear to be different than the rocks we had seen. And by the way, just to give you an anecdote, a few months ago, a colleague of mine writes an email saying, I'm just completing now a review paper about Oumuamua, the comet Oumuamua. And I say, what do you mean by the word comet? We both know that there was no cometary tail, there was no gas around it. How can you call it a comet in an authoritative review about everything we know about this object? And this was supposed to be published in Annals of Astronomy and Astrophysics, the most prestigious journal in astronomy for review papers. And he said, well, I have this theory that the object had a cometary tail when we didn't look at it, and it didn't have a cometary tail when we looked at it. And I said, well, that's just like going to the zoo and insisting that an elephant is a zebra and the stripes show up only when you don't look at the elephant. So to me, it's really strange to see experts or people that are describing what we know about Oumuamua. These are experts that worked on comets for decades, trying to bring it to the realm of what they are familiar with without justification. That's not the way science should be done. We should be completely agnostic. If something looks different, we should say it. But it reminds me of the story about the emperor has no clothes, where just a kid that didn't do any political calculations said what he sees. I feel very often like that. I'm trying to stay a curious kid rather than pretending that I know the answer in advance.
Hidden within this is a solution to the Fermi paradox that aliens are present. They're just simply small, quiet, and hard to detect. And that seems like actually one of the more reasonable solutions to the Fermi paradox.
Oh yeah.
But
I should also say that in the past, for 70 years, we followed the footsteps of Frank Drake, who suggested looking for radio signals about 72 years ago, and he passed away in September 2022 this year. And that is just like waiting for a phone call. Okay, and it's one method of looking for alien civilizations, but another approach, which is completely different, has nothing to do with the Drake equation, is to check your mailbox whether you have any packages that accumulated over time, because any spacecraft that is launched with chemical propellant would move at a speed that is smaller than the escape speed from the Milky Way galaxy by at least a factor of 10. So it will remain bound gravitationally to the Milky Way. The Milky Way will collect all the spacecraft launched over the past billions of years in great difference from radio signals that are moving at the speed of light. And if they were sent 1 billion years ago, before we came to exist, they passed by the Earth when primitive life existed on Earth. We were not around, and they may be 1 billion light years away by now. And most likely space probes or spacecraft were launched close to the end of the life of a star that hosted those civilizations, because at that point there would be a huge exodus from the habitable planet, and we didn't hear their cries for help because they took place before we came to exist. But if we look at interstellar space, we might find those crafts that left mostly in the last phase of the civilizations that realize that their star is about to eliminate any prospect for life on their planet. So they launched a huge number of crafts or probes to, and obviously cried for help at that time.
Now, Occam's razor here, everybody's going to invoke that, but I think maybe this has changed in that given the age of the Milky Way and the Fermi paradox, where Fermi's like, it was predicated on the idea that they should be here. We should see evidence of them. And yet we don't. But in this case, is it the simplest answer that there is some sort of a presence here in this way? Is that the simplest answer in this case?
Yeah, I think so. And I think Fermi himself did not do anything to look out. He basically had lunch at Los Alamos and asked, where is everybody? And, you know, it's just like sitting at home and looking around and saying, where are my neighbors? I don't see anyone. And of course, you need to look through your windows, and you better use a telescope to find them. And we now know that a significant fraction of all stars have a planet like the Earth, roughly the same separation. And we also know that most stars from 5 billion years ago. And we also know that within 1 billion years, the sun will burn the surface of the Earth, so we could not maintain life as we know it on Earth. And if other stars from 5 billion years before the sun, they went through that already. The surfaces of habitable planets like the Earth were burnt out by the red giant phase. These stars are now white dwarfs, perhaps, and obviously will not hear a radio signal from an Earth-like planet that was burned up by the star. So just expecting another civilization to be exactly at our technological development phase and communicating with radio waves is very naive. But if you search for probes, especially those that took part in the exodus from the planetary system when the star became a red giant before it turned into a white dwarf, when you look for those probes, you might find them around because they were collected over cosmic history, over the history of the Milky Way galaxy, over billions of years. It's a completely different approach to search for packages in your mailbox, and it was never attempted. So what I'm saying is we just used the wrong method. And what I find really strange is that the SETI community, engaged in radio searches for many decades, is quite hostile to the search for physical objects. And I find that surprising.
Well, I think we got caught up in a mantra. Extraordinary claims they require extraordinary evidence.
Well, my point is that extraordinary evidence requires extraordinary funding. So without investing the hundreds of millions of dollars that are needed to conduct this research, you will never find the evidence. And it's a circular argument to claim the evidence is not here without funding it. Now, I must say that I was struck by the fact that after publishing my book, not only that I had almost 2,000 interviews with members of the public that are extremely excited about this subject, and I was able to receive funding from donors that came to the porch of my home and were inspired by my book Extraterrestrial without doing any fundraising. So not only that, but I realized that 2/3 of Americans believe in extraterrestrial life, and that's more than the fraction that believes in God, which is slightly less than 50%. And obviously those people who became wealthy in recent years as a result of the internet and so forth, they represent the population, and a significant fraction of them finds this subject exciting. So I don't need approval from people who are entrenched in traditional practices, who are following the beaten path. I'm happy to explore the path not taken, the road not taken, the words of Robert Frost. And the reason I enjoy doing that is that it may represent low-hanging fruit, because if nobody took that path, nobody picked up the low-hanging fruit.
And the low-hanging fruit is an interesting idea because for some reason there has been an aversion to close study. But at the same time, there have been computations that go into it and suggest things like microprobes, where a probe is deposited in the solar system by a passing star system through a close encounter of stars in the past, or something like that. And those ideas were okay, but when you get really close, as in the atmosphere with us, that's where the aversion starts, which is taboo, as we discussed before. Now, what is the current state of the Galileo project in looking for UAP? I mean, you've got one instrument going. Are there going to be others? Is the funding there? Is the project moving forward?
Yeah, we're at a very exciting phase right now where the the suite of instruments that we assembled over 1 year is starting to deliver data. And that's just over the past couple of weeks. And we are storing the data and plan to analyze it with our computer system using artificial intelligence algorithms that will basically identify the nature of the objects that we see in the sky. And we're taking a video of the sky in the infrared, the optical, radio, and audio, 24/7, all the time. And then obviously we will see a mixed bag of objects, and there are two categories that come to mind. One are natural objects like insects, birds, perhaps rocks in the form of meteors, or meteorological events like thunderstorms. But one can also imagine human-made objects such as weather balloons, drones, airplanes, satellites, rockets, and we want to figure out if there is anything else, because even if one object out of many happens to represent a technology that we don't possess, that is not human-made because it performs in ways that human technologies cannot reproduce, and it's clear that it's a technological gadget because it has screws on its surface, we have a high-resolution image of it, then I would argue it must have arrived from somewhere else and it's extraterrestrial in origin. So that's what we are trying to find. Is there any outlier? Now, it's very different than the task of the US government. The US government is engaged in matters of national security. They want to identify objects that might be used for espionage, that are human-made, and obviously they are not a scientific organization. They don't care about something that came from another planet, because that something will not have a national agenda. It will not adhere to the borders between nations here on Earth. So suppose the US government notices something unusual, and suppose that was reported to the President of the United States, I would find that inappropriate, because it's just like telling the President of the United States, most of the ordinary matter in the universe is hydrogen. We just figured it out. And why would that be the privilege of the President? I mean, this is something about the cosmos that all humans should be aware of. So it's a result of scientific advice. It's nothing to do with national security. That's why I think that this subject of looking for something outside of this Earth should be handled using the scientific method of open data and shared with all humans, because it will tell us which reality we live in. And that's important for humanity as a whole. It may actually unify us, because if we find a smarter kid in our block, it will convince us that all of our differences are meaningless. The differences among humans, that the tendency to feel superior relative to other humans, which pretty much shapes history, human history, will be ridiculous, because here is another far more advanced entity out there, and we better relate to each other as equal members of the human species. So the way I feel about it is, it will be of scientific value, it will unify humanity, because it will give us a distant perspective about our planet, just like the image of the blue marble from the Orion spacecraft. And that's what we should aim to. It's, the way I see politics is as divisive, as basically emphasizing the differences among humans, whereas science brings humans together, because the knowledge should be shared by everyone, and it's a collaborative process of gaining that knowledge. So I would much rather prefer to see humanity glued together by scientific discoveries than separated apart by politics and national concerns. And one way to get to that goal is for someone to visit us and tell us, you are all one family, treat each other better.
Well, we become the humans instead of nationalities and things like that. The future is where we go to space, and when we go to space, we can't afford these things. We have to be the humans and do it collectively. That's space exploration. Now, I'm here to ask you this. A government, and I'm loath to go in this direction, but I will. If a government found a piece of alien technology, it seems to me that they would want to keep that secret, number one, because they can back engineer it and one up another nation state. In other words, the US recovers an alien artifact, They're going to be like, that technology is very, very advanced, more than anything we have, so we have to keep it secret, and we have to back engineer it. Presuming you can even figure it out. Do you think that that's something that may have happened? I mean, there are all sorts of rumors about Roswell and recovered artifacts even in private hands. And do you think that that's might be something that might have happened?
Well, I don't know, and I find it unlikely because over the years, over the decades, such information will be leaked. And the more likely explanation to these stories, these reports, are that one branch of government is developing advanced technologies that remain secret. They don't want other branches of government to be fully aware of them. So they are testing them without others knowing about them. And then when others are noticing them, they don't want that information to be revealed. So that, I think, is a much more likely occurrence where either private citizens or some military personnel notice objects that represent the future of human-made technologies that are produced either by other nations or by other sectors of government, the military complex. And this may have happened over and over again throughout history, and so some of the reports may be that. I find it hard to believe in a conspiracy. I don't think it's likely. I think someone would have provided a leak that would have been convincing. So far, it's all very fuzzy. We don't have good data or information that anything like that happens. And I say, okay, instead of asking the government to declassify information, which is pretty much like waiting for Godot in Samuel Beckett's play, you can wait forever. It's much better to take action to our hands and just explore the sky on our own, or explore any object that lands on Earth that came from outside the solar system, like these meteors. And I'm just planning to do that. And the sky is not classified. We can just do this research and figure out if we see anything unusual. However, I don't want to go into military conflicts like in Ukraine or near military facilities, because lots of things are flying out there. There is a lot of noise, and one important aspect of doing good science is to reduce the noise level so that you can get a high signal. So if I were to select the place on Earth, if I were to look from above on Earth and search for unidentified objects, I would look, for example, at the South Pole, where you have ice. It's completely white. There is not much human-made objects flying over the South Pole, not many animals. You don't have trees, you don't have landscape that complicates your images. So it should be straightforward to see dark objects on the background of the ice. So that's an example where I would much rather minimize the noise level and not go to Ukraine, for example, where there is currently military conflict. And not everyone agrees with me. There were some astronomers from Ukraine that reported seeing dark objects in their sky and were arguing that they are at a distance of 10 kilometers and they are the size of 15 meters, and they move at a speed that exceeds the escape speed from the Earth, up to 15 kilometers per second. And I wrote a short paper saying that cannot be the case, because an object moving at 15 kilometers per second of that size would have produced a fireball. We know that from meteors. You cannot move through the atmosphere so fast without producing a huge ball of light. And therefore, that you cannot imagine dark objects that are darker than the sky. They should be extremely bright. And a simple way to interpret the data that they were reporting is to say they got the distance wrong because they measured it from one site, one observing site. And if the distance is 10 times closer, then the object would be a meter in size, moving at up to 1.5 kilometers per second. And that's what artillery shells are doing. And if they're even closer, they could be birds, they could be insects. So you need to pin down the distance. And of course, some people say, well, maybe it's new physics. And I say, well, it's not so easy to come up with new physics. These objects will be dark only if they block light. and then that means that they are interacting electromagnetically with light because they block it, and the interaction with electrons in the atmosphere would also be electromagnetic. So it's very difficult to imagine an object that blocks light but will not block electrons that are moving against it and produce a fireball as a result. And I should mention that a decade ago, in 2011, for example, there was an experiment that reported that neutrinos move faster than light. And within 6 months, it was found that there was a loose cable in that experiment called Opera. And in fact, neutrinos were completely compliant with the speed of light limit, even though there were lots of papers written in between during those 6 months trying to interpret the huge implications of a new physics. And so it's not easy to discover new physics, and when you have a highly uncertain distance measurement, you better check your measurements before you declare that you saw dark objects that violate the laws of physics.
Now, as I recall, one of the most interesting points of the play that you mentioned is, as I recall, Godot never showed up. So what happens if we have a null result? Is that useful in telling us that there's just nothing to the phenomenon?
Well, I should say we just invested $10 billion in the Large Hadron Collider. Why did we do that? Well, first of all, to prove that the Higgs boson exists, which was pretty much old news from the 60s. But the more exciting news that was hoped for is to discover supersymmetry, which over the past few decades was a very popular idea in the minds of mainstream physicists. They argued, well, there must be supersymmetry out there to solve some problems with standard particle physics. And the fact that supersymmetry should be discovered by the Large Hadron Collider because that's the natural range of parameters for that theory. And so $10 billion were invested to search for supersymmetry, and in fact it was suggested that the most natural particle for the dark matter would be the lightest supersymmetric particles. So we invested $10 billion, we searched for supersymmetry, and guess what? We didn't find it. Okay, so you might say, well, it's just like searching, waiting for Godot and not finding it. And in this case, it's not waiting, it's actually $10 billion. So why wasn't the claim for supersymmetry considered extraordinary so that we are not supposed to take it seriously until there is extraordinary evidence? Well, the answer is extraordinary evidence requires extraordinary funding. Okay, so this is an illustration where the mainstream agreed that it's worthwhile to $10 billion toward finding an extraordinary or substantiating an extraordinary claim, and ended up not being right. So sometimes science of the mainstream ends up at a dead end and does not find what it's looking for. And I should say it goes both ways. Sometimes we discover things where we didn't expect them to be. And just as an anecdote, between 1935 and 1939, Albert Einstein, at the prime of his career, made 3 mistakes. In 1935, he wrote a paper where he argued that quantum mechanics doesn't have entanglement, doesn't have what he called spooky action at a distance. That was his view. And then a few years later, he argued that gravitational waves do not exist. And then he wrote a third paper in 1939, arguing that black holes do not exist. And over the past 5 years, the Physics Nobel Prize was awarded to 3 major discoveries by people who proved Einstein wrong. So first was the discovery of gravitational waves by the LIGO experiment. Second was the discovery of a black hole at the center of the Milky Way galaxy. And third, this year, 2022, the Nobel Prize in Physics was awarded to the experimental discovery of entanglement. And I say Einstein did the right thing. He had his own views, he made mistakes, but he explored the frontiers of physics by taking risks and making assertions that were proven wrong. And these assertions deserve the Nobel Prize, even though we've proven them wrong. okay? What many physicists are doing now is not engaging with experiments. You know, you have, for example, the study of extra dimensions, string theory. They don't make any predictions that can be tested by experiments over 5 decades, 50 years, the duration of a career of a scientist. So we don't know if these ideas are correct or not. These are the ideas would not be proven wrong, and therefore they will never deserve the physics Nobel Prize. And so doing experiments to test ideas is the bread and butter of physics. However, some theoretical physicists prefer to live in a theoretical construct that will never be proven wrong, because then they can demonstrate their intellectual abilities, their mathematical skills. They can show off without being proven wrong, and that's a much more satisfactory outcome for them. They can get honors, awards, just by demonstrating that they're smart. But I say physics is not about that. It's not about showing off. It's about learning about reality. And the way we learn about reality is not by having a monologue of telling reality what it's supposed to be without testing the idea, but instead, it's a dialogue where we learn from experience, from experiments, where we hear nature talking back to us. And the example of interstellar objects is a case where we discovered the first objects from outside the solar system where they look different. And here is an exciting frontier where nature is telling us something new, and nevertheless, it's being ignored, pushed away from the mainstream, because it doesn't quite fit what experts that work on rocks know. And we say something is wrong with this approach, where we live in virtual realities that complement our ego, and that's part of the mainstream. And at the same time, when evidence shows up that shows objects that we've never anticipated, that's not part of the mainstream.
Now here we are in a completely different area of study. The idea of alien communications using gravitational waves and potentially detecting that. You recently came up with an idea with another author of a lunar gravitational wave detection. Could you tell us about that, and how might we use that for study?
Yeah, so here on Earth, the main limitation of LIGO is seismic noise in terms of going to very low frequency gravitational waves. I should preface that by saying that just like electromagnetic radiation or light that we see, gravitational waves come in different wavelengths. We can see light all the way from blue, short wavelength, to red. And by the way, blue light scatters in the atmosphere of Earth much more than red light as a result of light scattering, and that's why the sky is sort of scattered light. That's why the Earth looks blue from a distance, from the vantage point of the Orion spacecraft. That's why the sunset is red, because the blue light is scattered. It doesn't make its way through the thick atmosphere that covers the horizon. And the red light makes it through, so you can see the sunrise as red. So light, we know, comes from different wavelengths. There is infrared, there is ultraviolet, and the same is true about gravitational waves. And the reason LIGO focused on wavelengths of order 100 kilometers is because that's the characteristic size of the horizon of the black holes that are made by the collapsing stars. So when you make such black holes that weigh tens of solar masses, and they collide and produce ripples in space that are the gravitational waves, and those ripples have a wavelength at the most bright phase of the emission that is of order 100 kilometers, hundreds of kilometers, which is the frequency range or wavelength range of LIGO. Now, the question is what happens at much longer wavelengths that are radiated by, for example, black holes that are much more massive. We know that the centers of galaxies have such supermassive black holes. The Milky Way has 4 billion solar masses in its central black hole. I should say that together with the postdoctoral fellow, Fabio Montucci, we recently discovered a black hole of roughly the same mass at the outskirts of the Milky Way in the dwarf galaxy B01 that is about 1 million light years away at the edge of the halo of the Milky Way, and has about 3 million times the mass of the Sun. So these supermassive black holes, if they come together, they emit gravitational waves that are millions of times longer wavelengths than those detected by LIGO, and how can we detect them? And one way is to go to the moon, because the moon doesn't have geological activity, doesn't have seismic noise. And moreover, LIGO built these vacuum tubes where the lasers are propagating through, so that the laser beam does not get scattered, and we measure a slight contraction in the path length of the laser when the radiation waves is passing through. And if you go to the moon, there is a natural vacuum out there. You don't need to produce these very expensive vacuum chambers where the LIGO experiment operates. And so it came from two effects. One is that there is no geological activity, no seismic noise, but also natural vacuum. There is no atmosphere at all. And we suggested to build a lunar gravitational wave detector, and we ended up concluding that it would be extremely sensitive also to the kind of wavelengths you expect from more massive black holes with a wavelength of the order of Earth-Moon separation, for example. So very large wavelengths. And it turns out that one can, in principle, imagine searching for technological civilizations if they are producing gravitational waves of that wavelength. But I would say it's a long shot, because just to give you an example, if you ask what kind of amplitude of gravitational waves you would get from the biggest impact of a meteor on Earth. So let's imagine the asteroid that killed the dinosaurs. It was roughly 10 kilometers in size, the size of the city, and it came from the sky, collided with the Earth. Such a collision would generate a gravitational wave of an amplitude that would be detectable from the moon, and also of the right wavelength that I was talking about. So a moon observatory could detect that, but it's a huge, massive object, and humanity is unable to accelerate our position. An object of that mass, that is roughly 10 kilometers in size, moving at the escape speed from the Earth. So we cannot really, with existing technologies, produce a gravitational wave signal that would be detectable even from the moon. But if there was a much more advanced civilization that would, for example, bring a Jupiter-mass planet close to the black hole at the center of the Milky Way galaxy, then we could detect that. But that's a huge cosmic engineering project, and I would hesitate to imagine it's.
In other words, we have a long way to go as far as resolution goes with artificial intelligence. But is there a way, perhaps long in the future for Earth space, for detect things of that size? For example, is there an alien civilization out there saying, well, that planet got hit by, or didn't pass by an asteroid, and a sort of record that dinosaurs is propagated?
What I'm hoping for is that if we ever build sufficiently sensitive gravitational wave detector in the right wavelength, that we might detect a signal that involves the equation that unifies quantum mechanics with gravity. And that, of course, will not only be significant in terms of revealing a very advanced civilization that is capable of major cosmic engineering projects, but it will also advance our science. And of course, you can hope for such a message from an intelligent civilization, but in principle, we can get such a message also from what is called naked singularity. That's just like the central region of a black hole that is not hidden from us by an event horizon, which is the name of your program. Usually an event horizon hides the singularity of a black hole, so we can't see it. A singularity is the place where Einstein's equations that describe space-time break down, and where quantum mechanics is needed, where a theory of quantum gravity is needed. So if we ever see a naked singularity, we would look straight in the face of quantum gravity. And that is one way to learn how to unify quantum mechanics and gravity. There is one such event in our past, which was the Big Bang. And the question is whether we can ever look all the way back the naked singularity of the Big Bang. And one thing that was produced at that extremely early time was gravitational waves, actually, of very high frequency, very short wavelength, roughly the wavelength of the cosmic microwave background, about a millimeter. And recently I wrote a paper together with Sunny Vagnozzi where I suggested that we can actually test what happened in the very early universe by attempting to detect this graviton background. Just like the photon background, the cosmic microwave background left over from the Big Bang, there should be a graviton background, just like the neutrino background left over from the Big Bang. So this graviton background should be filling space and representing the very early instant of the Big Bang. And there is a way to detect it by using a very strong magnetic field that would convert it to an electromagnetic signal. So we suggested doing that. Now, why is that interesting? Because there is a very popular theory in cosmology that is called cosmic inflation, which basically says that the universe early on, after the first instant, went through vast expansion, exponential expansion, so that a tiny region became the entire observable universe that we have right now. That explains why different parts of the universe have roughly the same conditions in them, even though they didn't have time to communicate after the early times. So cosmic inflation is a very popular theory, and indeed, if it happened, it would have diluted the graviton background that I was talking about. So one way to test cosmic inflation, to rule it out, is by detecting the early graviton background. And that is really a unique way of doing that, because so far, cosmic inflation could potentially lead to any type of universe. In fact, there is this notion of the multiverse, that an eternal cosmic inflation throughout many regions of space will end up producing anything that you can imagine. Anything that can happen will happen an infinite number of times. That's a consequence of eternal inflation, which was coined by Alan Guth, the pioneer of cosmic inflation. So that's, on the one hand, allows you to explain anything that is observed in our universe, but at the same time, it makes the theory not falsifiable. You can't rule it out, because if it can accommodate any fact about our universe, you would say you cannot rule it out. So what we did in this new paper is offer a method of ruling out inflation simply by detecting the cosmic graviton background that would not exist in any model of inflation, just because of the vast dilution of the cosmic graviton background by a period of inflation.
Now, to switch gears and go a little bit deeper, more philosophical for a moment. When you look, as a cosmologist, when you look at the universe and you see things, we were talking about naked singularities, there seems to be prohibitions, governors on the universe somehow that, at least as far as we can tell right now, prevent us from seeing a naked singularity. There's always something. Or, for example, time. Time travel seems to be prohibited simply because it would violate causality. Things like that, rules. What do you think of those? Einstein once would vaguely refer to it as the God of Spinoza and the Old One. What's your view on this?
Well, there is a cosmic censorship that suggests that naked singularities do not exist. And since we don't have a theory of quantum gravity, it's just unclear whether it should be satisfied. I mean, obviously, if there is a naked singularity, we are unable to predict what will happen as a result, because we don't have a theory of quantum gravity. In one of my essays, I said that perhaps what happened before the Big Bang is that there was a scientist in a white coat in a laboratory that knows quantum gravity and knows how to engineer the birth of a baby universe. Perhaps our universe was created in a lab. That's an interesting possibility, because if our universe allows advanced scientific civilizations to be born in it, they would eventually realize how to unify quantum mechanics and gravity, and they would give birth to a new baby universe, and so on and so forth, just like many generations of people will continue indefinitely by giving birth to babies that eventually give birth to new babies and so forth. So In principle, that's a possibility. We don't really know all the rules about our universe, and of course, one shortcut that we can take is to find others who know them, that developed science for many more years than we did. Because we know two things. We know that we arrived only over the past few million years, the human species, the Homo sapiens, here on Earth, and that's a small fraction, one part in maybe 10,000 of the age of the universe. So we just came at the end of the cosmic play, and the universe existed for 13.8 billion years before us. And the second thing we know is that we are not at the center of the cosmic stage. And so to me, that says a simple thing. It says, if you are not at the center of the stage and you arrive just at the end of the play is not about you. Okay, that's a message that is difficult for humans to digest because we are often driven by our ego. And here the universe is telling us, stay modest, keep being guided by humility because you are not that important. And over the centuries, we just refuse to accept that message. We still refuse because not many people within academia are willing to study seriously the possibility of signatures of extraterrestrial technological civilizations. And for example, the textbooks on cosmology never mention life. They consider only dead objects. They imagine a universe that is lifeless. And that's pretty arrogant to say we are the first intelligent beings since the Big Bang. So my point is we should instead try to learn by looking out, because in the context of the matter content of the universe, we prefer to believe that most of the universe is made of the same material that we are made of, that we find in the solar system. And then it turned out that 84% of the matter is dark matter, of a substance that we don't know, we don't find here in the solar system. And moreover, matter is just a third of the mass budget in the cosmos right now. There is also dark energy, and that's maybe the vacuum energy density, cosmological constant. We don't know what its origin or nature is. And so what I'm saying, we already learned that lesson, that only 5% of the cosmic mass budget is ordinary matter. Now we see interstellar objects that came to the solar system from outside. They also look different from the rocks that we found in the solar system. So, you know, when you walk on the beach and you are used to finding rocks or seashells that are naturally produced, and suddenly you see a plastic bottle, you better not insist that the plastic bottle is a rock of a type that you've never seen before. You better not insist that it's a rock. You better not call Oumuamua a comet just because you are used to working with comets and that gives you a warm, fuzzy feeling. You better say, well, it doesn't look like a comet. What is it?
It's sort of like walking along the beach and you see a Pepsi bottle and you immediately say to yourself, that's a weird clam. It just doesn't make any sense at some point. But let me ask you this about quantum gravity. This has been elusive. Einstein spent the better part of his career really trying to figure out some sort of quantum theory of gravity, and we're still not there. Is it possible, and this has been suggested, that maybe gravity is not of this universe and that it's actually leaking into our universe, which would explain its weakness, from a parallel universe hovering just above ours? How do we test these kinds of alternate ideas about gravity? And if we can't test them, then are they pie in the sky and we'll simply never know?
Yeah, I mean, we need to come up with experimental tests. And if we don't come up with them, then we cannot make progress. And it's possible that, I mean, we've been practicing physics for the modern physics for just a century, and it's possible that we come up with a bright idea. But my view, based on the history of quantum mechanics, that experiments will be the ones to educate us. And so if you ask about the fundamental nature of gravity or the unification of quantum mechanics and gravity, as of now, we imagine it being relevant near singularities, for example, near the center of a black hole or the Big Bang. And if we had more data to guide us about those events, information in the black hole, or that is not hidden by an event horizon, or just somehow learning about the singularity, the naked singularity of the black hole, or detecting the graviton background from the Big Bang. That would definitely tell us something about how quantum mechanics and gravity are unified. So as of now, these are the only places that we can imagine, but in the future there might be some unusual experimental evidence. For example, if the nature of dark matter represents primordial black holes, or represents some quantum gravity effects in the early universe, or if the dark energy represents that, figure it out, we would know that. I can even imagine seeing spacecraft that have engines that use dark matter as fuel, so that discovering them would tell us something. So I think we should behave as humans, that trying to seek evidence from nature, because the world of ideas is vast, and reality represents just one out of many possibilities. And in order to figure out reality, we better get some data or evidence that guides us. And of course, you can put goggles on your head and live in the metaverse, and you may always look like Brad Pitt in the metaverse and have a warm, cozy feeling about yourself and the reality that you live in. And you can also do the same, not just by putting goggles, by taking recreational drugs. But my suggestion is that we better engage in the actual reality. And I would love to see the pimples on the face of reality. I don't think reality is under any contract to flatter us, to be the most beautiful that we can imagine. It might actually be very puzzling, like quantum mechanics is. In my mind, true love represents trying to learn about things that you haven't wished for in your partner, that are surprises, that represent your subject of love. And I love reality, and that's why I'm a scientist. I want to learn everything about it. I don't want to imagine what it would look like if it was beautiful, if it was as beautiful as the mathematics that I can imagine exploring. That's not really what I hope for. And if you think about the dates, if you were to imagine your partner being some idealized version of what they actually are, that's bad for you for two reasons. First of all, you are not adapting or attending to the needs of your partner because you are idealizing your partner. Second is, you are not responding to the reality that you partner with, and that would lead to a lot of friction later on. So I'm saying the best form of love is learning about your partner and accommodating. And in terms of the reality that we all share, that's science.
It is, but there are also divorce proceedings, so the universe is not beholden to telling us exactly how it works. And it just seems at times to be very puzzling, very bizarre, and that we may never have a complete understanding of it. But above and beyond that, what are your thoughts on black holes and the extreme distortion of space-time around them? Do you think that there are paths in physics that are within general relativity and all that could lead us to backwards time travel possibilities?
I think there is a fundamental problem with that, because if you were to go back in time, you could reconstruct a history that violates your existence. You could do things that would make your parents never conceive you, never, so that you would, and that's a logical inconsistency. Okay, and now you might say, okay, well, maybe if you were to go back in time, you would never be able to make those actions that would violate your future. So maybe, but a much simpler solution would be to say we cannot go back in time. And now, frankly, I would not be saddened if we can't go back in time, because as long as we enhance our ability to repair the human body and have much longer life, that's a substitute. If there is this statement that life is meaningless, I have a problem with that, because even if life has very small, tiny sense of meaning in it, we just need to extend the longevity of the lifespan indefinitely, and then we would empower that meaning. It will change everything. And so altogether, I think Rather than imagine time machines going back in time, we should work on repairing the human body, updating it, substituting for it, and making our quality of life better. And that would be accomplished with the AI revolution that we'll go through, with the biological revolution that we'll go through as we augment our bodies. But perhaps we can get a shortcut by meeting an extraterrestrial civilization.
Now, what of, in regards to time travel, what of the implications of the many worlds interpretation of quantum mechanics? Does that provide an out for the idea of breaking causality? Does that provide an out for the possibility of doing it, that if you travel back in time, you just end up in a different reality than what you were living in?
Yeah, so it's possible that one interpretation of quantum mechanics is that it represents many pathways, and you select one of them when you collapse a wave function. We don't know for sure. We have no clue as to how to interpret quantum mechanics. That's one of the fundamental puzzles of modern physics, and it may well be that the answer lies in the combination of quantum mechanics with gravity, because that's another thing that we don't know, how to unify the two in a way that is reliable, that makes predictions that can be tested. So rather than guess or make speculations, I would wait for more guidance, or try to find a smarter kid in our cosmic neighborhood that knows the answer, because that would save us a lot of time.
Now, my last question for you, Dr. Loeb, is related to the Galileo project. And it's something that keeps me up at night. Not really, but we'll figuratively say so. What if Godot finally shows up and you find something? How do you author a scientific paper and publish it in a major journal announcing the discovery of something we were previously unaware of that is apparently of alien origin?
Yeah, so let me first start from the confession that at that point, I wouldn't care much about how many people approve it, who knows about it. Just the knowledge itself would occupy my mind. And then, of course, sharing it with others is a duty for me as a scientist. But most importantly is the actual finding and the realization of the consequences. So I would ponder on that. And after that early phase where I think about the implications, I would let everyone know about it and also discuss what it is and what the implications might be. The implications could be huge to the future of humanity, because it could bring new knowledge, scientific knowledge. It could give us a sense of what the future might be like, save us time, change our aspirations for space, change our notion of our place in the universe, and change the relationship of humans to each other and the world politics and everything. And would change academia, obviously, because immediately there would be new areas of research, and everything that we applied in the past to humans will now be humans' extraterrestrial interactions. And as an example, if we find a gadget that is from another civilization that has artificial intelligence, then we might use our own AI systems to interpret their AI systems, because they might have kinship to their AI systems more than to us. And it would be interesting to watch that process of us trying to interpret. I should say that I don't count on physicists figuring out AI astronauts, because physicists are accustomed to dealing with non-intelligent entities, physical objects. If I were to interpret an AI system that came from another planet, I would much rather use psychologists. And they are used to dealing with intelligent systems, or use AI systems that have no prejudice, or just let them figure it out. Anyway, there is a long process of interpretation of the intent and the purpose of anything we find that is functional, how to respond to it, who represents humanity, all kinds of questions beyond the impact that it would have on our psychology, on our aspirations, on our beliefs. So it would be huge. And because of that, it's just like when Galileo discovered that the Earth moves around the sun. They put him in house arrest. Even if today they would have canceled him on social media, it doesn't really matter. That's the reality that we live in. We know that the Earth moves around the sun. And irrespective of how many people believe in it, how many people know about it, that's the reality. And so that's the first thing that will come to my mind, that here is the reality we live in. Whether people accept it, whether they like it, is completely irrelevant. And then, of course, there is a sense of duty to inform other humans of this finding. Just because I'm a scientist, I need to tell them so that it will become part of their reality as well. And that would be the process of writing papers. And frankly, once again, I don't care how many reviewers reject the paper from publication. That's irrelevant. The fact that Galileo was put in house arrest didn't change the fact that the Earth moves around the sun. So what matters to me the most is the evidence. If the evidence is conclusive, it's irrelevant how many people dismiss it, it's irrelevant how people react to it, but you have to go through this process. And even if people will not be convinced in my lifetime, if I'm convinced, that's good enough for me. That will bring me a sense of fulfillment and a different sense about my future after I die, because I would realize that there is much more out there. You see, the way I think about death is our body is just like a physical object. It's just like my computer. I was asked a question by Ralph Blumenthal, the New York Times reporter, a few days ago. Aside from the question of what was before the Big Bang, there are two other questions. What were you before you were born? He was asking about me personally. And what will you become after you die? And I told him, there is a trivial answer to each of these two questions. It's the same answer that you give to the questions, where was my computer before it was assembled? And what will happen when my computer stops working? In a way, the raw materials existed before the computer was assembled, and the computer will go back to those raw materials when it stops working. And the same with my body. I don't see any difference. But obviously, in the long run, what matters is how much farther can we advance our knowledge and extend the longevity. Just like repairing a computer and upgrading it and replacing parts, we might be able to replace parts in our body and extend its lifespan. And that would eliminate the question of death from our lexicon and would change our society, of course. So my personal fate is not particularly important. My personal knowledge is not particularly important. And that's true for every person. But what really matters is what is the reality that we live in. And that's what I hope to find in my lifetime.
Reality is reality, no matter what. And we have to understand it as it is, or do our best to try to understand it. But the reality is that when you look at things like death, there's either something after or there isn't, but it doesn't really matter, because if it's just the state you were in before you were born, well, wasn't unpleasant, at least my experience of it. And if there's something, then we suddenly understand the universe, but not while we're living.
Well, the thing about death is you can tell people whatever they want to hear, and nobody came back to sue you if it turned out to be wrong after going. Yeah.
It's true. I have not been sued by the deceased. And that I actually find that comforting in a way, that there are people that will never sue me in this world, or were in this world. Dr. Loeb, it's been a pleasure. Everybody can find links to Dr. Loeb's essays, his book, Extraterrestrial, and everything in the description below. And I think this is probably over 10 times we've done this now, Doctor, and I look forward to another 10.
Well, I should say that in August, at the end of August 2023, I will have a new book published. It's called Interstellar, and I would be delighted to discuss its content with you once it comes out. It's already on Amazon very early in the game, and so there are lots of things to wait for.
Indeed, and we will talk about it. But I would also note, too, Life in the Cosmos, your textbook that you wrote with Manasvi Lingam as well, which is sitting on my shelf.
Thank you.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.